Hello everyone, this is lesson 5 of our digital graphics course, unit 30, and in this session we're looking at the second part of the theory-based digital graphics unit. I've called it part 2, but really it's a continuation of our first lesson here. So we're going to look at the theory behind digital graphics. Okay, so we've looked at bit depth and what that means already, but just as sort of by way of a bit of a recap, bit depth is how much color information is stored for an image. We looked at this in lesson 4, but here you go again. I'm just recovering it for you again. The information's on the screen. So basically, the higher the bit depth you're going to have, the bigger the channel. Human eye can only register about 10 million colors. Okay, but each color in an 8-bit image has 256 possible colors. Okay, so each single bit will have 256 possible colors that you can choose from. That's why in Photoshop, if I try and choose an R, when I showed you that in the first tutorial, it will let me choose a value of red between 0 and 256. Okay, so there'll be 256 different versions of that color I can choose, and then 256 different versions of the green, 256 different versions of the blue, which gives us this true color 16.777 216 possible colors. Okay, 16.77 million colors. So that just clarifies a point earlier. So this is our activity at the bottom that hopefully some of you managed to do that I didn't point to, but basically it makes 2 to the power of 8, which gives us 256 colors. That's how it's calculated. So we looked at this version before. So basically this is the potential colors that these systems all had access to. Okay, which is very interesting. So the original Game Boy actually only had 1 bit per color, so that gave us 8 potential colors that we could use. The Nintendo DS had 6 bits per color, so we were talking about 262,000, and then the SNES had 5. So this was how these Nintendo systems have progressed. So when we talk about color space, okay, so this is a little bit advanced, but if you are interested in how color space works, so this is the capabilities that a particular device, certain devices are able to show a certain amount of colors. So some screens will say that they can show more colors and are more vibrant and so on. Okay, so when we talk about like Ultra HD monitors and so on, they've got the capability to show more of the color space. So basically it represents what a camera can see, how much the monitor can see, how much of this color spectrum can a color monitor display, or a printer, and so on. Basically, these color spaces such as RGB or CMYK, HSV, and stuff like that, they all have different types of colors. So like a printer will be on a CMYK because that's for print, but RGB is for a monitor. RGB is possible color that is made up from red, green, blue. We spoke about this before, but this is the color space. And inside we can see what these different, like an Adobe RGB can see this yellow triangle, they can see that, but a ProPhoto RGB can see all this information. You see there's still some missed out, but this D65 white point can see this information, and sRGB can see all this information. So we've got a certain range of colors in this color space that are available. This is going a bit deep, you probably don't need to include this in your assignment, but I'd like to give you the information anyway. Image capture, obviously we looked at before, but when we talk about image capture, okay, we're talking about this sort of information that's relevant. Okay, so DPI stands for dots per inch. Basically, dots per inch is the measure of how many printed dots on a printer they can put on a piece of paper. Okay, so basically how much detail, so how close together can those dots be? That's how rich the image can be. So if you imagine you can do 1 dot per inch, that means you can only put 1 dot for every inch on that bit of paper. But if you do 100 dots per inch, you can do 100 dots every single inch. That means you can have a lot more close together dots that you'd barely be able to see that was a dot, and it would look like a straight line. So that's how you get the information. And then pixels per inch is obviously when we're talking about on a screen. So rather than talking about dots on a printer, we're talking about pixels on a screen. So it'd be the amount of pixels the file contains. So it represents a certain height or width and so on. So how many pixels are in every single inch. So if you measure an inch of your screen, how many pixels are there in that inch of the screen? And lossy versus lossless we looked at before, but I just wanted to recap all this. So lossless obviously is where we don't lose any information. We can press the size down, but it remains quite big, and then it comes out the other side exactly the same. Lossy, when we talk about doing things like streaming over the internet and so on, we will start with a massive image. We'll compress it right down so it gets smaller, really small, and then it will come out the other side, but it will lose a certain amount of information. If you remember the examples we looked at before, and here's some information on it if you do wish. So let's look at these examples here. So file sizes vary on the file format. So if we take this file, for example, that I downloaded and saved as some different versions, okay, so just saved exactly the same image and saved it with different settings, okay. So I chose a file. So a good activity for you to do is if you've got GIMP or Photoshop at home and stuff like that, you'd be able to save a file and save as all these different versions. Look what it does to the file size. You'd think the same picture would always be the same regardless of file size, but it's not, because each file size compresses image differently and stores it. So if I saved it as an uncompressed TIFF, if I saved it as uncompressed TIFF, it's 901K. Lossless TIFF actually gets bigger, which is obviously not losing information. High quality JPEG, medium quality, a web quality, so I'm losing quite a lot of information there. Changing the resolution, so JPEG, which is low quality with massive compression, a PNG, and a GIF. Okay, so these are all different. Same image, this example, but a massive difference in the file sizes that we're getting out of it. And obviously the quality will differ as well. And then just to recap again, we spoke about optimizing. Okay, so you need to consider where the image is going to be used. Is it for print or web? If it's for print, yes, we're going to need to store plenty of information on it because it's going to print out. We might print it out A4, we might print it out, A3, A2, we might print out massive. So it's going to need as much information. But if it's on the web, I don't want it to be any bigger than it's going to display on the screen. There's no point storing it as this big if it's only going to be this big on a screen. Just make it that big then. Don't store any more information than you have to, because someone's having to download the information and having to display it. Basically, this output, the optimization, is going to impact the bit depth, resolution, dimensions, etc. So whatever you're outputting to, whether it's print, web, or however it's going to be displayed monitor, that is going to impact your choices for bit depth, resolution, dimensions, and so on, because you're going to know how big you need to store that information. So a good activity, if you've got Photoshop at home, is to use the save for web function to see what quality is lost when you save, and what, but how good an image still looks. A save for web is designed for when you you store a photograph and you want to just display it on an internet on one of your websites or something like that. It still looks great, but it optimizes it really, really well to store information. Okay, don't worry about that activity because we're not doing Unit 37. You'll be doing that in your second year. However, that's the end of our theory-based tutorials. I really hope that these have been informative and they give you enough information to cover all of the tasks for Assignment 1. If you've got any questions, please do ask, but that's the theory for Unit 30 completed. Okay, thanks very much.